this. Hello everyone. So I've attached the PowerPoint slides, and then I've also attached this as a PDF for you. This is about relative velocity, by the way. Before we start relative velocity though, I want to go back. On the last video, I asked you to do this quick check at the end, and we got the first one right, but we didn't get, I think it was collective, that we did not get the second one right. And I think maybe it was just some keywords that we were missing. So on the quick check for the uniform circular motion, it says that a particle moves along a path and its speed increases with time. In which of the following cases are its acceleration and velocity vectors parallel? So I think everybody hands down said when the path is straight, and I completely agree with that. But the next question says, from the same choices above, in which cases are its acceleration and velocity vectors perpendicular everywhere along the path? That key word in this question is everywhere along the path. And I think that most people said when the path is circular. And I would agree with you if they'd said that when the path is circular, moving at uniform constant speed or moving in a uniform constant motion. But that is not true if that path is circular and that speed is increasing. In that case, it's not going to be, in that case, I'm not going to see my acceleration and velocity vectors be perpendicular everywhere. So I could be moving along some type of curved motion, and if it's speeding up, remember we're going to get, if my velocity is not constant, I'm going to get some overall total acceleration vector. So I may have a radial component, and I'm going to have some tangential component, and then maybe the overall velocity vector, that total velocity vector, isn't just necessarily going to be perpendicular to the speed, to my velocity. So because of that, I can't say that my motion, when the path is circular, will always produce acceleration and velocity vectors that are perpendicular everywhere along the path. And that's because if my speed is increasing or if my speed is decreasing, I'm going to get some tangential and radial components for acceleration now, which means that I'm going to get some total acceleration vector, and that means that it may not necessarily always be perpendicular to velocity everywhere along its path. But we know when the path is circular and uniform circular motion, then I know that acceleration and velocity vectors are perpendicular everywhere along the path. So I have to be careful about that wording here. So technically my answer for this second question would be never. So if you still have questions on that, let me know and we can talk about it again tomorrow, or post on the blog. We can have a conversation about that on your blog as well. Okay, so we're going to talk about pretty much just relative velocity and something called frames of reference. So relative velocity and frames of reference. We've kind of been doing this, I think, or you've been doing this maybe in your own mind, but we want to give maybe some variables for it and just talk about specifically just what a frame of reference is. So I can think of a frame of reference as, or I would say a frame of reference can be described by a Cartesian coordinate system for which an observer is at rest with respect to the origin. So let me say that again. A frame of reference can be described by a Cartesian coordinate system for which the observer is at rest with respect to the origin. So in terms of frame of reference, we can say that two observers that are moving relative to each other usually don't agree on the outcome of an experiment. And their observations, though, are related to one another. So in this case here, I have two different observers. I have observer A and I have observer B. And I have a point here, P. So observer A can measure point P 5 meters from the origin. So if I just make point A, if I make observer A my origin, then I could say then from my origin, or from point A, they see point P just 5 meters away. Observer B, though, if I look here, if I make observer B my origin, observer B actually measures point P 10 meters away. So for my frame of reference, it's going to be different based on where my origin is or based on where I'm measuring it from. So frame of reference here, I have my observer A, observer B. I see that my point is different based on where I'm at on that Cartesian coordinate system. So it's different just because I'm using different frames of reference. Okay, on this case, I have a man that's walking on a moving beltway, and a woman on the beltway sees this man just walking what would be for her at moving normal walking speed, because she is on the beltway and he's on the beltway and they're both moving together. So if he's walking also on this beltway, it looks like he would just be walking at normal speed. But I also have this stationary woman that's standing off to the side that's not on the beltway at all, and so she's going to see this man, she'll observe this man walking even faster, with a much faster speed, just because of her frame of reference. So, and she sees that because I have a combination of this beltway that's moving, and then also this man walking on the beltway that's also moving. So this difference is just due to their relative velocity and their frames of reference. Okay, so we can generalize relative velocity and reference frames. So reference frame for SA is stationary. So I have a reference frame here for SA, and then I have another one here, another point that we have here, B, SB. So I have a reference frame SA, and I have a reference frame SB. SA is going to be stationary, SB we're going to have moving. So I can say that the reference frame for SB is moving relative, or is moving to the right relative to SA. So here's SA, I have SB moving to the right at some velocity. So I'm going to call that velocity, it says VAB. So how do I read that? The first subscript, when I have my 2 letters denoted there, my first subscript is going to represent what's being observed, and then my second subscript is going to represent who is doing the observing. So first subscript represents what is being observed, and the second subscript represents who is doing the observing. So I would say that this is the velocity of B as measured by observer A, if I had VBA. In this case, I have VAB. So I could say that this is the velocity, of A as measured by observer B. So let me just repeat that the first subscript represents what's being observed, and then the second subscript is just telling me who is doing the observing. So I'm observing the velocity of A, and it's measured by observer B. So that's what that's saying.
Excuse me, teachers, I have a couple of quick afternoon announcements.
Okay, in terms of my, I'm sorry that Mrs. Prince is talking over me, but we're going to just keep going. In terms of my diagram here, so I have my 2 reference frames. I know that B is moving relative to my reference frame A, so it's moving at some velocity here in some amount of time. I know that my position I can call my position from A here to P. I could say that,
Lannery Shea Cowan.
because I'm going to wait until she's done reading these names. I'm sorry.
Juliana Rizzo. Colin Moore. Adam Woosty. Justice Brock. Niles Johnson. Nope, it's Niles Jackson. Caitlin Elliott. Brendan Ruddy. Presley Richardson. Jacob Wisby. Kyle Puck. William Palmer. Emily Gold, and Zachary Foreman. Please come to the office. Thank you.
Okay, so I have some position vector that I have here between A and P. So I have like a displacement here. And my RPA is just representing the particle's position vector relative to A. So this is just my particle's position vector relative to this reference frame A. This is my particle's position vector relative to frame B. And then I have, again, that velocity or that speed that it's moving from reference frame A, I see here moving towards the right to reference frame B, and that's within some specific time. So I can relate all of these three vectors together, and Galileo is the one that started to work with this, and we're going to call them, these specific things are called Galilean transformation equations. So it says the positions as seen from the two reference frames we can relate through the velocity. So I can say then that my position vector of particle P relative to reference frame A is equal to that position vector of particle P relative to reference B, and then plus my velocity vector times time that we saw in this last one. So let me go back. So we have our RPA is going to be equal to these two components added together. So that's what I see here. I can take the derivative of this. If this is my position, I could take the derivative of that to get my velocity, and then of course I could take the derivative of that to get my acceleration. So that's what they're talking about here. So you should know by now our U's are representing when we have the derivative of that. And again, I can take the derivative of the velocity equation to find the acceleration, and let's do an example really quick. So I have a boat crossing a wide river, moves with a speed of 10.0 kilometers per hour relative to the water. The water has a uniform speed of 5 kilometers per hour due east relative to Earth. If the boat heads due north, determine the velocity of the boat relative to an observer standing on either bank. So I'm going to take this off because I need to write out the example, draw a picture. So if you can, print this out or like pause this so you can write this down really quick. Will you close that door for me so nobody comes in? Okay, so let's write out what we have here. Okay, so I know that I have or they tell me that I had a velocity of the river relative to the Earth. So I'm going to call that VRE. So I have the velocity of the river relative to the Earth, and I know that it's moving towards the east. So I have this river, and I have a boat. I have my little boat here, and that boat's moving due north, it said. So I know that my boat, relative to the river, has a velocity, boat relative to the river. So I'm going to call it boat relative to the river, and I said that, or the question said that that was moving north, and they want me to find the velocity of the boat relative then to the Earth. So I want to know, since I have my boat relative to the river and my river relative to the Earth, I could find, this would be the velocity of the boat relative to the Earth. So they gave me that the speed for the velocity, or the velocity of the boat relative to the river, was 10 kilometers. They told me this was 10 kilometers per hour. And I know that the velocity of the river relative to the Earth was 5 kilometers per hour. So my goal is to just find this. And of course this is at some angle which we can just call theta. So to find my hypotenuse, I could just do Pythagorean theorem. If I did that, I would find then that the velocity of the boat relative to the Earth should equal 11.2 kilometers per hour. If I asked you to find that in meters per second, you should be able to convert that to meters per second. That was one problem I think that we had on the first question, part 1, or part A and part B on your quiz from Friday. We had a hard time converting. So make sure if you need that extra practice, let me know. We'll do some extra practice with it. And of course I want to find that theta. I want to find that angle at which that boat is moving relative to Earth. So I could find theta, of course, by doing my inverse tangent. And that would be of my velocity of the river relative to Earth over that velocity of the boat relative to the river. And then you should get an angle of 26.6 degrees. Okay, so ultimately the math is pretty simple. It's just really trying to get this new notation that we have here by using these relative reference frames or frames of reference. So we're going to do some practice, or I'm going to give you some homework practice with this tomorrow. If you have questions, like I said, email me or post on the blog. I will see you guys tomorrow. Bye!